video addresses the one sample t-test, how it's used, and how it is compared to a one sample z-test. The particular study that we're interested in investigating here is to find out whether statistics students have a bigger memory capacity than people in general. So what we did in terms of research methodology is we read a list of 20 words and asked students to listen to them, and then we asked them to write down as many words as they could remember. The words were read at a rate of 1 word per second, and the score is the number of words that students reported that they were able to learn. Now we compared this to the working memory capacity that Miller found in his landmark paper, where he talked about how the working memory capacity of an adult human is 7 plus or minus 2 chunks of information. So we will use that when we're computing our one sample t-test. Okay. So the very first step is to figure out what the populations are, the comparison distribution, and the assumptions. The population of interest is people in general who have been studied by people like Miller to find their working memory capacities. Our other population is people like statistics students. Our comparison distribution is the distribution of means. Again, remember that we're talking about comparing a sample mean to a population mean, and so we need to use the distribution of means. However, in this case, in contrast with the one sample z-test, we don't know what the the population standard deviation is. So we have to estimate that. So that's one new thing that you'll notice is different about the one sample z-test or t-test in comparison to a one sample z-test. We also have our assumptions. So the next thing to talk about is the assumptions. And you notice that the assumptions are identical to the assumptions that we've had for the one sample z-test. The first is that the distribution is approximately normal, and the way that we can assure that through the central limit theorem is that we have a sample size of at least 30 or greater. Now it is robust to violation of that, so if you have a smaller sample size and it appears that your sample seems to be pretty normal, then you can proceed. If you couldn't, then you could use a non-parametric version of the t-test. Random selection is used. Again, that's another assumption. In this case, we don't have random selection. We used a convenience sample of statistics students in a particular class. So we have to be cautious of generalizability to students in general who take statistics. And the last one is that the dependent variable is scale, and the number of words that an individual remembers is a scale variable. So we've met that assumption as well. So here we're going to state the null and the research hypotheses. And we're interested in a one-tailed test, and you'll notice that symbolically here in the bottom that we have the population, the first population is less than, so our students are less than or equal to the population in general. Because our research hypothesis, the interesting one, is that we see that those students actually are going to have a higher working memory capacity than the population in general. So our null hypothesis is that statistics students have a smaller memory capacity or the same memory capacity as the general population. And in the research hypothesis is that statistics students have a greater memory capacity than the general population. So you'll notice that the null hypothesis has to have that equivalent, that same, and then the opposite direction of the research hypothesis. In step 3, we're determining the characteristics of the comparison distribution. So from step 1, we know that the comparison distribution is a distribution of means. And now we have to determine those characteristics. So we want to know what is mu, what is the population mean, and what is the estimated population standard error. So we've already stated, it's a given from the research that we're comparing this to, that the mean of the population is also the mean of the distribution of means, and that is 7 chunks or 7 pieces of information. In order to get the standard error for the distribution of means, we have to take the standard deviation of our data and divide it by the square root of the number of observations in our sample. So we're using our sample to estimate what the standard error is in the population. And we're even using that to estimate what the standard deviation is in the population. And remember that the denominator, when we estimate the standard deviation in the population, has a correction in it now. And so we use n minus 1 as the denominator because we're likely to underestimate the variability in the population. So we know that the standard deviation is 1.67, and we also have 16 individuals in our sample, and so that yields a standard error of the estimate of the standard error of 0.42. So I have the distribution here, and we're getting it ready so that we can draw in where our critical value cut points are later on. So right now I've just noted that our mean of the distribution of means is 7, and that the standard error of the estimate is 0.42. So now we're on to step 4, where we determine the critical values, or our cutoff. In this case, because we have a one-tailed test, we notice that our null hypothesis is that our students are lower than the general population, and our research hypothesis is that they do better. They have a greater working memory capacity. And again, that null hypothesis has the equal sign. Now our p-value, our alpha, our type 1 error rate, is 5%, or 0.05. So because this is a one-tailed test, we put that entire 5% type 1 error rate into the upper tail, because that's where the research hypothesis states that the sample is greater than the general population mean. You can also think about it, when you think about the numerator, you're taking the sample mean and you're subtracting out the population mean. So in this case, if you think about how the sample mean has to be greater in order for your research hypothesis to be correct, then you have to put that critical value in the upper end of the distribution. So here we can put our values on the distribution, and in order to do that, we need to come down here, and this is our one-tailed tests for the t-table. You notice that we have in a single tail, our alpha is 0.05, and our degrees of freedom, remember we had 16 people in our sample, so we have 15 degrees of freedom, because our degrees of freedom is the number of people in our sample minus 1. That gives us 15. If you come over here, we have a critical value of 1.753. So we can put that right over here and say our critical value of 1.753 is here, and this is our 5% all in one tail. So if our calculated t-test falls within this region, so is farther above the mean, more extreme than this value of 1.753, we can reject the null hypothesis. We found a significant difference. But we have to compute our test statistic before we can make that determination. So that's the next part. calculating the test statistics. So let's list out the givens in this particular scenario. We know that the mean of the distribution of means is 7 based on Miller's research. We also know that the standard deviation that we've estimated for the population is 1.67. The mean of the sample, our statistics students, is 8. And the number of statistics students we had in that sample was 16. So let's go ahead with the computation. And again, I'm going to talk about how we get that standard error first. So the standard error, like we talked about before, is computed by taking the standard deviation estimate and dividing by the square root of n. So we find that our standard error is 0.42. Now, in order to calculate the z-score, we take the mean of our sample, which is 8, and we subtract out the mean of the population and then divide that by the variability, which is the standard error, the estimated standard error. So we take 8, subtract out 7, and divide by 0.42, and we get 2.38. So this is our calculated z-statistic. We're almost there. In this next part, I've replicated here what our calculated z is. We have our critical value, and then we've plotted where that score falls, and it's 2.38, and it does fall in this shaded region. So therefore, we reject the null hypothesis in this one-tailed test because our value that we calculated for the t-test is more extreme or further away from the mean than our critical value of 1.753. So we can conclude that statistics students had significantly higher working memory capacity, the mean of 8, than people in the general population, of a mean of 7. And here we've reported that statistic with the degrees of freedom, and then we have the actual calculated t-statistic, and then we have our p-value being less than 0.05. So just as a reminder, now that we've talked about two different one-sample tests, the one-sample t-test is used when we know the mean of the population mu, but we don't know the standard deviation of the population, and we have to estimate the population standard deviation. This is in contrast to the one-sample z-test, which we use when we know both the mean and the standard deviation of the population. Those are both given to us. So next time we're going to be talking more about the dependent samples t-test, which is another type of t-test that's very similar to how we compute a one-sample t-test and a one-sample z-test.